Welcome back to our series on statistical mechanics. In the rest of the series, we develop statistical mechanics on a classical route. For that route, one of the critical aspect is the density function. So, in this episode, we will introduce the concept of density function. In the previous episode, we discussed the concept of ensembles. For example, if you remember, the canonical ensemble was represented as something like this, where we were having macro states with constant n, v and the t, and you allow the energy to vary. And for example, in this particular ensemble diagram which I have drawn here, you can understand that there are 4 different microstates which are involved in this ensemble at an instant of time, right? 1, 2, 3, 4 microstates. Now, we need to get in ourselves into this classical route of solving the statistical mechanics and its development, right? So, therefore, one of the platform where we need to utilize is the platform of phase space. So, you must have learnt already the phase space in your classes on classical mechanics, right? So, exactly the same concept of phase space is being utilized in the statistical mechanics for its classical development. And if you remember, the phase space, which we otherwise call by the name gamma space, is a 6n dimensional space, right? So, what all it compresses? There are 3n dimensions of position, which we generally represent by q, and then there are 3n dimensions of momentum, which we represented by p, where n is the capital N is the number of particles in the system, right. So, this is the brief outline of the phase space. When we were discussing the phase space in the classical mechanics, we know that this phase space and the components in it, the position and the momentum is comprised in a space which is defined by the Hamiltonian, something similar to the energy, right. So, the Hamiltonian H So, this phase space is limited by a hypersurface which is created by the energy Hamiltonian. And we know the expression which we learned there was that in classical mechanics probably was that Qi dot is equal to dou H by dou Pi, and Pi dot is equal to dou H by dou Qi, right. Pi dot is equal to minus dou H by dou Qi. So, these are the expressions connecting the Hamiltonian with its dimensionalities, which is the momentum and the position vectors. Now, extending this concept into our statistical mechanics, we can always represent this Q and the P for explaining the microstate. So, therefore, we tell that in the statistical mechanics, the QP, right, QP represents a microstate, or if I have more number of possibilities, I can always put a I here. Qi Pi defines a microstate. And the hypersurface which we were talking about, right, which I can draw it like this, and it is defined, its boundaries are defined by the energy or the Hamiltonian, and I can always spot some point in this sphere of 6n dimensional space with vectors or with the coordinates q and the p. Right, and this point therefore can be termed as the representative point. So, in the hypersurface, the Qi Pi represents a microstate, and that microstate can now be represented in the hypersurface by a representative point, which are shown here. Now, a question could arise in your mind. So, how did we define the system? We defined the system at a particular instant, right. So, this diagram is valid for a particular instant of time, say t1. Now, what happens if the system moves or the time evolves? Say if the system evolves to say t2, what will be the what could be the variation or the development in the system? What happens is that at t1, if this is the representative point, I can always approximate that this point moves to another point in the same surface, which is limited by the Hamiltonian, and it can be represented by the new representative point like this. And as the time changes, this can go on varying like this, right, and so on and so forth, right. Yeah. So, this is the kind of change which we need to appreciate. Now, only thing which limits the movement is the boundary, which is the maximum, which is the Hamiltonian of the system, which is in the modern or in the later development we call it as the which represents the energy. Now what we need to do is that we need to evolve this picture for a similarity with this kind of an ensemble picture. That is one thing which we need to develop upon. So, let us see how can we do that. Now, for that purpose, I can always I need to always go back to the hypersurface which I was imagining. Now, let us represent this microstate. So, how many microstates are there at the instant t1? So, imagine that I have this position at time t1. This ensemble which I have drawn here is at the time t1. So, naturally I should be putting it the time t1 here also, and therefore, I can now extend this microstate which I represented by a cross over here, right. Now, I have the other three ones. Say if I represent this one by this symbol. Now, in this phase space or in this hypersurface, I might be able to spot it say somewhere like this. Okay. So, this element in the ensemble is now being translated into our new phase space like this, and for example, let this be something like that. Similarly, I can put the corresponding representative point. All these represents a corresponding representative points. For example, this is Q1 P1, this is Q2 P2, and this is Q3 P3, and say for example, this is Q3 Q4 P4. So, all the 4 different ensembles, the elements in the ensemble is now being represented in here, right. Now, as I told you, what will be the picture or the hypersurface at a later time T2? The same hypersurface, because with the time the energy is not assumed to change, but here definitely I can always assume that this position and the momentum or the representative points will change its position or change its representations in the phase space. For example, for this Q1 P1, at time T2 it may have moved over to this point. But here one thing you should always remember is that the so called version of the position and the momentum is valid only in the classical regimes. But when we move into quantum mechanical treatments, we are not allowed to define a particular position and a particular momentum at any instant of time. But classical mechanics allows us to do that. So, therefore, I can definitely put or assume that this point, the Q1 P1, has now moved into this point. And similarly, for Q2 P2, maybe it has moved over to here, Q3 P3 that moved over to here, and Q4 P4 may have moved over to here. So, the entire arrangement is now different, right. So, let me remind you one more thing. See, the whole picture of macro state, in the initial episodes I categorically told that at an instant of time a macro state can have only one micro state, right. Now, the concept of ensembles, instead of time averaging, it introduced the concept of time independent picture, which means that we are going to represent all the microstates possible in that macro state at the same instant of time. So, in this picture, which actually is translated from this picture which we drawn in the previous episode to here, this is a translation from here to the new phase space representation, which is a 6n dimensional space. So, therefore, now it will be really interesting to see how that happens in a, for example, in a chemical reaction. So, in a chemical reaction, you can always for example, if you have a box in which there are many particles, and these particles will start colliding against each other. Now, the only thing which this particle or the system will obey is that the whole energy of the system is constant. There will be collisions, but as you know, if one of the atom is stationary and a ball or a molecule which is having a velocity strikes against this ball or the atom, the second ball will be moving with the same momentum as which the first molecule must have transferred. So, but in the entire picture of this system, of the whole system or the whole ensembles, as we then the new terminology which we use is the same. So, therefore, the macro state the energy is the same. But if you look into the same into the individual atoms which are colliding, their energies will be varying. So, and therefore, with each collision the number of microstates will go on increasing, and therefore, the entropy will increase. So, this is after from T1 to T2 we can, it is always safe to assume that in the classical regime we have evolved from here to this one. Now my question is that in this hypersurface, if I ask you to take a imaginary volume or some volume, right, and ask you to count how many microstates are there in that volume, right. The question is clear. So, this is a sphere and I allow you to choose any volume in this hyper sphere or the the phase space, and ask you and I ask you how many microstates. This is 1, 2, 3, I have represented here 4 microstates for as representative purpose. There will be many more. I did not want to make the picture more confusing by drawing more and more microstates, right. So, if I ask you to take an area, for example, take a volume, for example, take this volume, right, and I ask you how many microstates will be there in this volume. So, this is a count. That count is valid for a particular time. As in this diagram, I am asking you to calculate it at time t2, and that function or that number which you will tell me the number of microstates in a random volume which we chose is what we define as the density function. So, this is what the density function. So, therefore, the density function is the number of representative points or the number of microstates in the volume, in a volume. So, here in the phase space in your classical mechanics classes, you must have always defined the volume by a particular volume element as we call it, and you must have written d raised to 3n q, d raised to 3n p as the measure of that volume element. So, the density function basically defines the number of representative points in the volume element d raised to 3n q, d raised to 3n p around some representative point q p. So, I can always so you choose I allowed you to choose a volume random and you told me a number, right, and then my question is that, so where did you choose it? Sir, I chose it somewhere here. So, I can always denote that point from at which you started your counting by a representative point, right. For example, this point. So, you took the volume around this QP. So, in short, the density function is the number of representative points in the volume element d raised to 3n p around the point QP in phase space, and this density function is in general represented by rho of q p t. So, this is how we represent the density function. So, density function is generally represented by rho of q p t, and therefore, if you took a if you took an area of say a volume of the d raised to 3 n q d raised to 3 n p, I can always write the entire the count or the number as rho of q p t d raised to 3 n q d raised to 3 n p. Yeah, so another way of talking about the density function. See, now the density function almost becomes a identity for the microstates in an ensemble, right. So, it becomes an easier representative tool basically. Now, when I was explaining about the density function, I defined at a particular instant of time. I asked you to choose a volume of your freedom at a particular time, say t2, right. Now, the density function offers more than that. So, basically it symbolizes the manner in which members of the ensemble are distributed among all possible microstates at different instance of time. For example, at t2 you chose this volume around a representative point qp. So, now at the next instant of time, say t3, I can ask you to recalculate the number of microstates or recalculate the density function for the same qp. So, that is also the density function, and then you can always compare the density function at say different times say t1, t2 and t3. So, density function allows us to compare how the members of the ensemble are getting distributed among different or the all possible microstates at different instance of time. So, then we need to take further the classical discussion of the ensembles and the representation with the density function, which we will continue in the next episode. Thank you.